Newport from Goldman Sachs, all sitting in there. We sit there and we pretty much throw tantrums in the community forum about your delinquencies. All right, and we're telling the big players. We're telling it to IBM. We're telling it to Oracle. We're telling it to Caractata. We're telling it to Red Hat. We're saying, look, Java is not a significant player for our use case. If you accommodate our use cases with something that's sound and complete, we promise you we'll be your best customer. We're everybody's best customer once you satisfy us. Okay, so it's being pushed by a lot of angles. Everyone's tired of auditioning and caching providers and writing their own facades to delegate to the proprietary APIs. We're sick of it. It's a delinquency in the Java community. It's shameful. So we want to give some incentive to these caching providers to write a standard. So maybe that's a little harsh, but that's how it is. Really? So. All right, let's look at it. It's okay. Finally, after years and years, Terracotta and Oracle designated 2 full-time employees, Greg Luck and Yannis Cosmopoulos, to develop the spec. It's developed completely in the open. 15 expert group members. 20% of those expert group members are from Wall Street. Okay. Lots of healthy debate. Lots of little flames go back and forth. It's civil, but it's intense. The spec is completely open, free to use and implement any way you see fit. The reference implementation that we're building is Apache 2 licensed, and the test for compatibility kit is also Apache 2 licensed, just for information purposes. Let's see. Expected implementers. Now, these are the big Java caching players, okay? You have Terracotta with their ubiquitous EH cache product. You have Oracle with Coherence. You have JBoss and the Finispan. IBM with Extreme Scale. A big contributors, SpringSource and Gemfire. You've got GridGain, you've got Tmax, you've got the Google App Engine and their Guava caching capability. Anyone use Guava here? It's very strong stuff. They're pledged to be JSR107 compliant. And you also have SPI Memcache and their Memcache client. Okay. Getting started. If you want to get started, we have our artifact up in Maven Central. So if you want to pull down our API, just put this tag in your build environment, and you can pull it straight down. You'll get our API. Looking at everything that we're doing, everything's out in the open. And in terms of code artifacts, in terms of the specification, all this kind of stuff, we have it all up in GitHub at this URL. Okay. Let's see. It's kind of blurry, I think. Anyway, if you look, this is our Java docs page for the 0.6 snapshot of what we're doing. Okay, if you look in the far left corner there, we have the package that's presented there on the main page, javax.cache. We have a rich set of annotations. We're building a capability so that if you want to write, if you have existing code that you want that code to be subject to caching consequences, you don't have to write JSR107 Java code. You can decorate your existing code with annotations from the JSR107 package, and those caching consequences, you have to be in an intercept, you have to be in a method level intercept, but those caching consequences will take place as a result of annotations. I can't even read that. What does that third one say? Cache event. We have a lot of cache event processing capabilities in our API. If you look down that left tree in the far west of the page, you'll see a bunch of interfaces that end with listener. Okay, we have a listener for just about every cache event. You create a cache entry, you can listen for it. You remove a cache entry, you can listen for it. You update, read, access, all this kind of stuff. All these listeners. But anyway, this is our Java doc page. We think it's going to be a pretty sound and complete and capable standard for doing caching operations with Java providers. Okay, let's see. All right. Looking at some of the features, one of the API is going to support atomic operations. It's going to support them both transactionally and in terms of entry processors for exclusive atomic compound operations. The methods are similar to what you'll find in java.util.concurrentMap. Okay, we have read-through caching. Okay, obviously. Okay, if you do an access and the data isn't present at this level, the API will transparently seek wherever to wherever it finds the hit. We have write-through caching. We have both synchronous write-through caching, which is where the flow control is kind of like not doing anything else but writing through to the back-end system of record. And we have what's called asynchronous write-through, which acts sort of like a write-behind capability. You can go up and do other processing while the implementation writes through to the system of record. We have a rich set of cache event listeners, and we have a statistics capabilities. One of our packages is called javax.cache.mbeam. So if you're using standard JMX mbeam, we have a package that gives you, this is turned off by default for performance reasons, but if you want, you can deploy and write your own mbeams that can interact with statistics mechanisms that we've set up in this package to measure caching statistics. Here's a huge one for us, and it's one that David and I fought explicitly very loudly for. Transactions, including all isolation levels. Now, a lot of these Java caching use cases are a bunch of kids worrying about, like on a distributed internet game, where their monster position is being cached correctly so that their shot hits it with the right coordinates. And like, you know, Netflix caching applications like 12 indexes into Schindler's List is to see who's watching Schindler's List simultaneously. That's fine and good, but those aren't high-stakes transactional ways to host data. We want to see if you are capable to host capital markets data, you know, international capital. Can we access and mutate safely with having our data cached in your solution? We have caching annotations, which gives you a nice way to have caching consequences in your code without writing literal JSR107 Java code. And we have generics. Everything's type safe, as you would expect with generics. Okay, here's a huge thing, huge for capital markets. The JSR107 compliant caching implementation is transactional in two important but different senses. All right, one, your compound access mutate operations against a cache entry are guaranteed to be exclusive and atomic, okay? Don't let them sell you that, oh yes, it's exclusive and atomic. They have to pass our test of compatibility, okay? If they don't pass the test, they're not JSR107 compliant. Okay, so don't worry about their sales pitch now. If they're JSR107 compliant, clause 1 is guaranteed. And here's another super important one. Compound operations against the cache are guaranteed to preserve transactional ACID properties. The full scope of traditional transactions are ACID properties. First way you can achieve it with the cache entry processor interface. Second way with the old, reliable javax.transaction.user transaction. To be JSR107 compliant, the caching providers are going to have an implementation of that, okay? Let's see what this means further. Okay, more important to note, all isolation levels are guaranteed, okay? Even your most extreme pedantic isolation use case, and only capital market use cases have these crazy pedantic ones that are like way out there in extreme. And the caching vendors don't want to hear it. They say, oh, our use case doesn't accommodate it. Well, our use case does. Do you want to be our caching provider? Or do you want us to keep paying $1 million license fees to KX Systems? Because we'll keep doing it if you're not sound and complete. We're not going to risk money on your caching solution. This is what this means, okay? TX read uncommitted. If you have no tolerance, or if you have complete intolerance, if you don't care, just specify, I'm willing to read TX. I'm willing to read uncommitted data. You can specify that, okay? TX read committed. If you are intolerant of dirty reads, like every financial use case is, okay, you can specify that you're dirty read intolerant by specifying that isolation level. Same for these other higher isolation levels that only exist for our use cases. I'm going to give you a quick example. Whoops, did I do this right along? Let's see, yeah. Okay, here's an example. Let's say I have this JSR107 JCache entry, okay? It's a savings account. I'm hosting $5 in the account, okay? I have two transactional threads. Transactional thread 1 is on the far west, time going downwards from the top. And transactional thread 2 is on the far east, going downwards from the top. Now let's say at time equals 0, the value in the cache is $5, and both threads begin transactions. At time equals 1, thread 1 mutates the value in the cache. It credits it $1. So the cache becomes $6, okay? Now, the container is obligated to mark that cache entry as dirty, okay? Because it was mutated without being committed. Now, going further, At time equals 2, thread 2 reads in the value, and it reads in 6. At time equals 3, both do more processing. But at time equals 4, transactional thread 1 that mutated the entry rolls back. So the entry goes back to 5, but it's too late. Transactional thread 2 had already read the value of 6. It commits with the value equals 6, and what happens? Your data is inconsistent. All right? This is a minimum capability that has to be able to be done by a caching provider. Otherwise, no financial use case will engage with it at all. You have to respect people who are intolerant of dirty reads. We're some of those people. Okay, how would you code it? I don't want to go into this too much great detail. It's very simple to code this. For transactional thread 2 to be guaranteed that it won't endure a dirty read, all it has to do is build its cache with a Java x.cache.transaction.isolation level read committed. It means I'm only willing to read data that's already been committed by your caching container. Okay? From there, you use the very familiar user transaction API from Java x.transaction to JTA. You construct a new version of your JSR107 provider's user transaction implementation with a reference to the cache that you just created with the read committed policy, and then you just process it. So when you do the cache.get on the account, you'll block until transactional thread 1 commits, okay, or rolls back. So here's how it looks. Here's how it looks when we execute that code. At t equals 2, we're not going to endure a dirty read. We're going to block because we're intolerant of dirty reads. And the container guarantees that we won't be given that access until the data that was muted either commits or rolls back. Now we see at t equals 5, the data did roll back, so transactional thread 2 will be allowed to access it, and it gets the safe value, the value that won't cause data to be inconsistent, the value that won't cause bankers' pagers to go off in the middle of the night and programmers to get fired. Okay. Now, how about other cases? Okay. Can we use JSR107 to accommodate all transaction isolation tolerances and intolerances? What about those rare transactional use cases that have extreme TX isolation demands? For example, if I have an intolerance to phantom reads, which occur without relevance nowhere but in the capital markets use cases. Okay. Answer is yes. All right. We are sound and complete with regard to accommodating all transaction isolation demands. What about multiple dynamic views of the same cache with different demands? Yes, we're sound and complete with regards to accommodating that concern. For example, let's say we have a retail desk and an institutional desk, okay, and shared in common is a cached high-yield credit portfolio of 3,000 bonds, okay? Retail desk does thousands of trades daily. Okay, each trade just a few milliseconds to transact. Average trade $5,000. All they need is read committed isolation. The policy of that desk is to churn and burn. Okay, if we get a phantom read, who cares? Just trade more. Okay, it's not going to cost us anything. On the other side, you have an institutional desk. Okay, these guys do the big bet the bank swaps. Okay, so if Credit Suisse is going to do a swap with Goldman, okay, and it's going to be a $10 million credit swap. Okay. We are intolerant of any retail trade messing us up, okay? So we specify transaction isolation serializable, and we're guaranteed that we won't have to worry about mutations in the portfolio done by the retail desk. For the 4 seconds that we need to conduct the metrics for a fair swap, we're guaranteed that we get it. Very, very important. Sound and complete with regard to all the transaction isolation use cases. All right, moving forward, how to please everyone. We have some features. Store by reference is a feature that we allow. Okay, in the typical map, it's a store by value. Store by reference, you get much better speed. XA and local transactions are an optional feature. Caching interception, that's also optional. We have a capabilities API, so you can consume what options are provided by the provider. Okay, so we have these two classes give you helper methods, and you can say whether or not the feature is supported in the provider. Okay, standalone versus distributed. If you're a standalone in a single VM, we can give you store by reference, the store by reference option, which gives you speeds similar to current hash map. Cache event listeners are very useful for triggering events in a standalone environment. If you're